Lecture of this morning session, which will be given by Phillippe Robert on the resource sharing algorithm with logarithmic weights. Phillippe.
Thank you. Okay. Is it okay like that? Okay. So I'm very glad to be back in this magnificent center 3 years after this program, as mentioned. And so I thank the organizers for this nice meetings in series. And I must say that this work is a direct consequence of the meeting we had 3 years ago. I will tell a little more during my talk. It was just that one of the SEGA invited us to give in a workshop for students in Edinburgh, so where several of us gave lectures, and during that time that I realized that we could do something on this subject. So this is a real consequence of this program. So I'm again grateful to the organizers for that. Okay, so it's a joint work with Amandine Weber, which is with the École Polytechnique. Okay, introduction. So this is an old problem. This is probably the oldest problem that you have in computer science. How do you share a resource between competing users? So the resource is a communication channel, computing power, whatever you like, and you have nodes competing for this resource, and each node receives a stream of requests to access the resource. And you need to devise an algorithms so that people ignore them more or less. So you're in this distributed context. So you cannot make global queue and say, oh, this is first in, first out, and no problem with that. So it doesn't work like that. You have to say how you use this resource. Okay, so typical example, wireless, where you have stations with some range. Oh, where is working? Okay, yeah, with the range of each mobile, and it creates some kind of a zone where within each of these red circles, only one station can transmit at a time, just because of interferences and this kind of thing. So a way of representing that, so you have streams of requests, J streams of requests arriving at the node, and you want to use this this frequency to transmit the data. So this is a quite classical context. What I'm interested in today is a specific algorithm, which is the F-sharing algorithm. So a node, if at some point the state of the network, meaning that Nj is the number of requests at node J, then it will receive a fraction of the capacity, and the capacity will be 1, just for the talk. And it will receive a capacity which is proportional to f of n of j, with the idea that f is increasing. The more you have requests, the more priority you will have. But you balance it with this function f. So the question is, how you choose f so that, we'll see that. Okay, so this is a general scheme of sharing resources. So a way of doing that in a wireless context is a very classical set, this random access. So each node draws an exponential random variable with parameter f of nj, and decide to transmit after this time if nobody else tried before. Okay, otherwise it stops. With this scheme, node j will access to the resource with this priority. Okay, so that's easy. And if you transmit for delta units of time, if your delta is small and some f of n of k are large, then this is almost the F-sharing algorithm, and in the same way that round robin is processor sharing. So this is the main idea. And this is a way of implementing that in a wireless context. Okay. Okay, so some examples. So what I would call alpha sharing, it's a little misleading because there are some alpha share algorithms, but I will try to avoid, but just quite convenient to call it like that. It just consists of taking a power function for x. Okay, so you take something proportional, something which is the power of your number of requests in your queue. And node j will receive this amount of capacity. And of course, if alpha is 1, this is a well-known processor sharing that everybody knows here, I guess. So the one I will be more interested today is log sharing. Instead, I will take the log of the quantity. Okay, so a node J will receive this fraction of the capacity. Okay, so the more you have requests, the more you receive capacity, but you just balance that. You don't increase completely as you would do with the alpha sharing. Okay, so the idea is just giving priority to big nodes, but not too much. And this is the idea of this, at least one of the ideas, where this kind of scheme is used. Okay, so literature is enormous. So you have historical references for random access networks back in the 60s or 70s, let's say. So there have been, at the turn of the century, many works around how bandwidth is allocated in TCP networks, and where you encounter also kind of such kind of algorithm. And more recently, wireless networks. So it's Damon's talk in Edinburgh in 2010, where I gave a talk on fluid limits of wireless networks. And, so this is, during Damon's talk, they had this idea that we should look at this problem. But there are Sam and his co-authors, so I have not seen Sam if he's around. And Dobravat and his co-authors studied also this discussion, and they are using also this log function to access the network. And they are using it also just because of the log, the dynamic of the log is smoother in some way. So there are some technical reasons why the log is also used in their papers. So Damon and Dobravat made a lot of work in this domain. So I can go, I can enter the detail, but this is the main picture of the domain. So the context. Capacity of the resource is 1, and I have J nodes. So I have Poisson rivals, exponential services, and rho J is the load at node J, and Lj of T is the number of jobs at time T at node J. Okay. So very simple. So there is something very simple. This is a work conserving policy. So there is no question about stability here. If the sum of the rows is less than 1, then it's stable. No question. So this is not an issue. What are the general questions? So what are the qualitative properties of F sharing? Why choose F rather than another F and so on? And what is the impact of F, more precisely? And so here I would like to mention that how can we compare the impact of the choice of the log on one side and a polynomial function on the other side? Okay. And what can we say about the invariant distribution? Because you know that's stable, but you don't know much about the invariant distribution, which is so Sam and his co-authors also did some work on delays in this in some wireless networks. So it's also related to that. Okay. And the tool I will use are scaling methods. So this is this is the main theme of this work. That with scaling method, you can begin to understand the phenomenon in these networks with the use of these functions. Okay, just a warm-up exercise. Let's say I will try to just to say what if I want to do fluid limits for alpha sharing policy, and I take 2 nodes. So if you write the stochastic evolution equation, so we have 2 nodes, L1 and L2, and we just write this integral equation, which is simply tells you that number of nodes at time t is the number of initially plus the arrivals, the average arrival, minus the capacity it has received, and plus the stochastic fluctuation here. So this is an exact formula. Mi is stochastic fluctuation. It involves compensator of the Poisson processes for arrivals and departures, and this is in fact the martingale. So this is the stochastic equation that you have here. And when you look at fluid limits, you look at the scaling. You speed up time with n, and you scale space with n. Okay? And the nice thing here is just because this function is homogeneous, if you multiply any Li by a scalar, it will not change it. So you will be able to write almost the same equation, but for this scaled process. and this is how it works. The scale process satisfies also a similar equation. Okay, and the nice thing here is that the stochastic perturbation here vanishes at infinity. So you end up with something which is like that, which is a deterministic integral equation. Okay, so but in this way you have proved, I just keep details of course, but it's not difficult, that these scale processes indeed converge, and the solution, when it's not zero, is a simple solution of an ODE. So this is what you would like to have every time you use scale process. Okay? So this is what usually you try to do when you scale processes, just that in the end you have some deterministic equation that you can study, and then from the properties of this deterministic solution try to say some qualitative properties about the stochastic process initially. Okay, so now the question is there an ODE scheme when I take a log? So this is the question. And Damon has a slide with a title which I liked at the time, the limits of fluid limits. So he presented us a series of simulations with a log, which were a little disturbing. And so the conclusion say, well, fluid limits are perhaps not the appropriate tool for studying this kind of function. Okay, so I will. The main answer is almost right. Is almost right. Okay. So I will start with a network with two nodes, which is enough, in fact. Once you understand the network with two nodes, you understand most of the mechanism behind this policy. Okay, so I have two nodes, and I have a jump process. So I have so just repeat what I say. In fact, just arrival rate and service distribution. And I don't have any problem of agonicity if the sum of the rows are less than 1. Okay. So what we did, I think we did like Damon. We started with simulations. And I explained I'm with simulation. Usually you understand things. And it's the first time that after the simulation we understood less than before. Just because Damon has a star network. And he had four nodes. And I say, well, that's too much. But we can't start with two. A star network with two nodes is not serious. So we'll take 3. And with 3, you have, as long as you don't understand what are the key parameters, you have just a range of strange phenomena that you cannot understand. So it's the first time it was not so useful. So we understood the simulations after we did the math, in fact, which is quite rare. Okay, so simulations consist of having node 1, which has a load which is less than half, and the other one which is 0.6. And to start with the weakest node at 0, and the other one very high. Okay, so saturated node for the second component. And if you do the simulation, then you end up with that. So L2 stays at its initial value because we're not looking at so much, and the load is quite close to 1. And L1 is just at this level for some time. Okay? And if you, so this is, if you look at on the log scale, you have that. The log scale, you see more easily this phase, in fact. And if you do that, you have a kind of growing phase, and then this stabilization. Okay? And now, if you want to focus on this part, you just look at not L1, but the exponent of L1 with respect to n. Then you have something like that, and then some oscillating picture here. Okay, so this is what you do. And when you have several nodes, you have this mixed together. So you have deterministic part and suddenly oscillating part and then deterministic, and it's difficult to figure out what's going on. Okay, and if you look at the complete one, because if you start with a stable network, it will return to 0. Then you have a curve like that with a similar shape here and here, except here it's a little noisy, as you can see. Okay, so that's the picture. It didn't help us much. It's funny to present, at least. Okay, so what we are going to do is doing some kind of surgery of this sample path, just by looking at the startup phase, the middle one, and the whole path in the end. And to do that, to do surgery, you just have to use different scalings. And so the scaling are like a microscope where you focus on the part of the sample size and you look with this microscope. So this is all what we are going to do. And the work we did was just to realize what are the correct timescales to use to study properly all these sample paths. So this is what I'm going to present you. So there will be 3 timescales I'm going to present you. So the initial phase, so this is in fact the key phase. It's a strange time scale. So here the t is an exponent. It's not a factor. It will be a factor when we will look at the fluid time scale. But here it's an exponent. Okay? And of course we'll look at t less than 1 because we don't want to go faster than the fluid time scale. Okay, so the key quantity for this algorithm is this one. So this is how, as soon as you realize that, things get more easier. So this is the beta 1 star, which is this quantity. And you start, as I said, with this node, which is at 0, and the other node, which is saturated. And the result is the following. If I with these conditions, then the process on the time interval beta 1, minimum 1, excluded, then I have a kind of deterministic convergence. It's converging to this function. Okay, so on this time interval, L1 is of the order of n power t. And as long as this quantity is positive, then L1 of nt is of the order of nt. And the first time this quantity is 0 is precisely beta 1 star. Okay, so this is where it plays a role. Okay, so and the beta 1 is less than 1 if rho 1 is less than a half. So the condition rho 1 less than half is playing a very important role in the following. So if rho 1 is less than half, then basically L1 of t is of the order as long as t is less than beta 1. Okay? So you have a first decomposition, your first description of your process. Yeah. Okay. Now, okay. So with that, I can reach any value n power t as long as t is less than beta 1. So what about the value beta 1 star? N power beta 1 star. So this is where it's a little more tricky, and this is maybe where this is a more complicated feature of this. If you look at the heating time of y, which is the first time L1 is greater than y, then the following result holds. If rho 1 is less than half, and you take delta strictly less than 1, and the first time you hit delta n beta 1 is of the order of n beta 1 again. Okay? And of course, you have log of 1 minus delta, so delta less than 1 is critical here. You do not reach n beta on this time scale with this result at least. Okay? And the proof is just some stochastic calculus and some drift analysis to do that. And so the important thing is that shows that this is in fact a tight result. This is the correct time scale of this event. N beta 1 again. And this will be our second time scale. So this is where we are using. So this is a very important thing. Okay, so what we explained is basically this part. I didn't say that what are the fluctuations. In fact, the fluctuations here are also deterministic. So it's this part of the sample path is almost deterministic. There are some fluctuations, but they are of third order, not second order, as it could be usually. Okay, so this is why you see this quite deterministic, more or less. It's a simulation, by the way. Okay, so now the second phase. So what we call the local equilibrium consists of looking at this time scale. So this is an important time scale too, because it just describes the way our process will live on this plateau that we have seen in the simulation. Okay, and the result is the following. Now I know that I can reach the value delta n beta 1. So I can with delta less than 1. Okay, so I start from this state, and I have a kind of law of large numbers on this time scale. Then L1 is of the order of n beta, and this is a deterministic function, h of t. And this deterministic function is simply the solution of some fancy equation like that, and h of t, so that the integral from delta to h of t of this is this quantity. So there is singularity at 1. So when t goes to the infinity, h of t is converging to 1. Okay? So we are almost at n beta 1 at the end of this time scale here. This is what it says. Okay. Okay. And there is a feature which has an important impact in the following, is that it's a slow convergence. And there is a problem. So, for example, you don't have a corresponding central limit theorem for this law of large numbers. You have to have some corrected. There is a central limit theorem, but it's a corrected version of it. And the main question is that you have a slow convergence. It's converging with a second factor of the order of 1 over log n, which is too slow for the time scale I'm using. So this creates problems in the following. Okay, so what we have is this equivalence. That on this time scale, I'm living on the multiple of n power beta, and I'm approaching it in some way. And the result concerning the heating time of the value n beta, integer part of course, is you have to add an extra log in your time scale. It's not a tight result because we know that it's a little below, but it doesn't matter here. So we reach this value n beta. Okay? Right. Now we are ready to say that we start from something which is of the order of n beta plus some fluctuation, which is of the order of this term. And then we have a nice central limit theorem, which consists of saying that when I look on this time scale minus n beta divided by this quantity, then I have a stochastic process in the end. And this stochastic process is a simple one. It's an Einstein-Uhlenbeck process. So it's a very ergodic process. So it explains the plateau that you see, that your process is around n beta, and you have a strongly ergodic stochastic process around this value. So this Einstein-Uhlenbeck process is playing an important role. So of course here I wrote it as a solution of the stochastic differential equation. B is standard Brownian motion, as usual. Okay, so this is an important feature of our process, this stabilization process through the Einstein-Uhlenbeck process. Oh, sorry. So what you can say, if I am at n beta, then on this time scale, my process will stay around n beta. Okay, but you know, we will have to look at on the fluid time scale. So this result is not enough just to draw conclusions. So this explains with quotes, of course, because you can't recognize the Einstein-Uhlenbeck process because I took the log, the exponent, but the fluctuating part is due to the Einstein-Uhlenbeck process that you see here. This is why you have this deterministic part followed by this fluctuation that when you do simulation, this is what you do. Especially if you have several nodes, there's some of them which are increasing deterministically, some of us are widely oscillating, and this is basically the phenomenon that you are observing there. Okay, now fluid time scale. Yeah, there is no choice. You must consider fluid time scale because it's on this time scale that the total the Q is emptying. You have an additive process, and the additive process fluid time scale is the natural one. Okay, so I will begin something which is not rigorous. Okay, so I'm assuming I'll start from n beta for L1, and L2 of course is n. And I'm making the assumption that my L1 is staying around n beta. And I will consider a small fluid interval, time interval. Okay, I'm assuming that on this fluid interval, it stays around n beta. So if it stays around n beta, it means that all the coming requests of class 1 are processed. So, and the coming request, this is row 1. So, not to receive the capacity left by this mechanism. So, the second queue received grows at this rate. Okay, just because you have a factor 1 minus rho, which is the capacity, remaining capacity for node 2. So if I look at my fluid scaling, then it just says that this is some gamma of t. For the moment, it has no importance. And then I can write that L2 of nt is gamma t of n. But I know if L2 is large, then my L1 is of beta. That. But there is a trouble, I assume that. So in some way, the local equilibrium of L1 has changed, and it's changing continuously with time. So here we have a classical problem of interaction of time scales between this time scale during which you have the equilibrium of the first component and this time scale, the free time scale. So you have an interaction. So this is a classical problem of interaction of time scales. And so these two time scales, and this is a stochastic averaging context, which is known. We have that in Loss networks, and it has been known for a long time ago. So in a stochastic context, its main references that you have Fredin and Vezan, but you have many authors before them, like Haspinski and others, and Papanikolaou, Suk and Varadan for some diffusion cases. So this is a quite classical context. And in the PD literature, it's a singular perturbation problem. You have a huge literature on that. Unfortunately, it doesn't seem to apply in our case just because of this slow convergence we have in the law of Lange-Jambos I mentioned before. And this is one of the problems we had. So here, how did we solve the problem? Just with bare hands, with estimation. And the main result of our paper is the following, is that if you start from an initial state L sub n, where L sub n is very close to 1 up to some constant k, kappa, then I can find a fluid interval where L1 is L2 power beta on the fluid time interval in the tube of diameter 1 plus kappa. So this is where I can control my L1 process, as I mentioned before. So this is really the key result, and it involves several estimations. The underlying phenomenon which is used is the ergodicity of the Archer-Uhlenbeck process. Of course, it's a discrete version because it's going to be Archer-Uhlenbeck process. But this is the ergodicity of the discrete Archer-Uhlenbeck process, which is used to say that these two random variables stick together sufficiently on this time, free time interval. Okay, because we cannot, the scale n beta log n is too slow for this time scale, so you cannot choose, and you cannot choose the stochastic fluctuation. You are lost with that. So the ergodicity is a key element here. Okay, so and then you can draw the complete picture because you say basically that this quantity is proportional to this quantity, and you have this nice curve that I have shown you before. Okay, so this is the end of the surgery, if I may say so. So next part of the talk we say how can we generalize that and how we can we use that. Okay, summary. So 3 time scales, and as I mentioned before, the first 2 time scales are the most important. 3 time scales is important, but it's natural. We'll have it. Okay, so coming back to Damon's comment that fluid limits have limits, but if you add other time scales, then you can have a comprehensive picture of what's going on. So fluid limits alone sometimes are not enough. I agree. Okay, so with that I can describe my network. Okay, so I draw my picture. So this is simulation by hand. No, just to so yeah. So this is my 3 time scale. So the time scale at which I read that, and the equilibrium, and then so the fluid is like that, and it follows on this with this factor beta 1. And I have assumed that rho 1 is less than half in most of the interesting results we had. I wish there were when it's not this case. If it's not this case, then this is a little more dull because they are both of the same order of n. We will receive each of them, we will receive a half. So it's a dull behavior. Not very interesting, but it's not difficult. So the interesting feature is that when one of the nodes is slightly less loaded than the other one, then you have an interesting phenomenon. And this is where that the problems are, at least the mathematical problems. Okay, and if you can do the same thing for J nodes. And you will have, depending on your conditions, of course, you will have J beta constant, and you will have J different space scales and J different time scales. But basically the same phenomenon will hold. Okay. Applications. So stability property of log sharing. So something which is, in my view, quite interesting, although not completely new, of course, but interesting. So I'm coming back to my alpha sharing policy. So I say that it was a solution of the ODE as long as it's not zero, of course. It implies, in fact, that as long as you didn't reach, in the case you are ergodic, of course, as long as you didn't reach 0, 0, 0, then both components are positive. Okay? And in particular, if your system is transient in the same order of idea, then both components diverge linearly with time, just growing. So there's a huge literature on that, on this kind of thing of the overloaded process sharing networks, for example. But this is an interesting feature, and it also for the alpha sharing model. Here, I'm back to the log sharing case. I'm assuming that it's transient. Rho 1 plus rho 2 is greater than 1, and that rho 1 is at half. Here. And I'm looking at this quantity, which is the capacity left when the first queue takes the capacity it needs. And it's easy to see that by just a stochastic domination argument that L2, this is the minimal capacity that L2 can receive. So at least the limit sup of L2 of t divided by 2 is less than kappa 2. In fact, it turns out that there is a result that this is exactly the rate of divergence of L2. And more interesting, that L1 is also diverging, but at very slower pace. It's at the rate t beta 1. So it's diverging, but at this rate. And the consequence is that L1 of t divided by t is converging to 0. Meaning that despite your system is transient, basically, node 1 being quite reasonable can transmit most of its requests through this, even in this overloaded system. Of course, it's not true. It's not stability in the Markovian sense, but it's in the thread. You process most of the requests on the time interval, and you just have a small backlog of this order of magnitude, which can be small if your beta 1 is quite is close to 0. And this is quite an interesting feature. It's not, and if you compare to alpha sharing model, it's completely different. In alpha sharing model, even if you are a node which has a limited demand, then you will diverge with all the others. When you use this log function, then you have a chance of transmitting your traffic without bothering if the other nodes are greedy or not. You don't care. So this is an interesting feature of this function. And this is what I call fairness, but I will not use it. There are so many experts in the room of fairness that I will not dare to use it without quotes, of course. So this is an interesting aspect of this policy, certainly. Second one. So what can we say about the invariant distributions of these systems? And so we'll present an heavy traffic limiter. And all of this is a consequence of the key result I mentioned before for the Fried limits. So I'm assuming that my rho 1 is less than half fixed. And rho bar is rho 1 plus rho 2. and I will let rho 2 such that this quantity is 1. So this is a heavy traffic context, no question. And I denote by pi sub rho, the invariant distribution of my process for rho. And the classical heavy traffic is not completely classical, but yeah, more or less, when I look at the sum, I multiply by 1 minus rho bar, it's converging to some exponential random variable. Okay? It's a classical result, heavy traffic result. In fact, this holds, but we have something much more refined in our case, which is the following. 1 minus rho bar L2 is converging to an exponential random variable. But same thing. 1 minus rho bar power beta is converging to the power of this exponential random variable. And again, it's the same thing. L rho 2 is diverging of the order 1 over 1 minus rho bar, but this one is diverging on the slower time scale, the slower space scale, sorry. Okay, well, and so it could create, if you think of waiting times as Sem and Scott has studied recently, it could lead to some problems with waiting times, because this queue will be quite more loaded than the other queue in the system at equilibrium. This can be a source of problems. Okay, so that's what I had to say. And all these results use, so I can say a little, not so much time. But we are using tightness and this result about the control on 3 time scale of the ratio L1 over L2 power beta. So now, when I change the log by an arbitrary function, what's going on? Basically, almost the same thing, provided that you have some conditions. So I'm back with a general function f, and I would say, there are growth conditions on f, of course, because if you take f of x alpha, you don't have these results, but you have growth conditions. So I do not detail them, but we mentioned in our work. And so, provided that you have growth conditions, then you replace this time scale, the initial time scale, by this one, and the other one by something which is more complicated to write in a small space, as would say some French mathematician from years ago, but it's not as difficult as this time. And so it's a little more complicated here. But you have the same basic phenomenon of this 3 time scale, and of course you have the 3 time scale after that. I just gave some examples of the local equilibrium, which was our n beta 1 for the log, becomes, if you take the log power gamma, it becomes that. And if you take, maybe I think the Rabat used it, log at some point, then you have this, this is where your second queue, the first queue is leaving, and you can see there that it's much more, it's smaller than the n beta 1, and so on and so on. So you can, basically, you can do modulo some technical conditions on the growth of the function f. You can do almost the same thing. So it's not specific to the log function. Okay, so I will conclude with the start network, which was the initial motivation which led us to this problem, which Damon mentioned. So I have j plus 1 nodes. The central node is j plus, j plus 1, and I have this node. So in a wireless context, all the blue nodes can transmit at the same time, but a blue node can transmit at the same time as j plus 1, the red node. So this was the idea. So the equivalent of the transition rates are the following. For a node on the outside, then it's proportional to the sum of the log divided by the total sum of the log. Okay, and the central node receives the capacity, which is simply the load of this node divided by the sum of the log of all the nodes. So this is okay. So I'm taking the set of parameters which is the most interesting in my view. So there are many cases, but this is so we assume that the central node is the most loaded. Okay, so rho j plus 1 is greater than all of them, and you can order the others. There is no problem. I'm assuming that all the nodes on the outside are 0 initially, and of course that the central node is loaded. And I will do the same game I did with my 2 nodes. Okay, so, and I'm looking at this time scale, because as we have seen with log, you should use this time scale. Then I'm plotting the exponent with respect to n of L1, L2, L3 up to Lj. So Lj plus 1 will remain at n, so its exponent will be n because we are looking at this time scale. And I have the corresponding beta j star for each of the row I have on my node. Okay, so I have a deterministic growth until I hit the first beta 1, but it's beta 1 divided by j because I have j nodes of the same kind and they are growing at rate t, so it's a jt, and I have this scaling. And the funny phenomenon here is the following, that after this time, the exponent of L1 is decreasing to 0. So there is a subtle thing here. There is a local equilibrium, so that, and then at some point, your exponent is going to 0. Okay, and it arrives at 0 at beta 1 over j minus 1. So this is a new, and this is technically this is where we have some problems because the exponent is depending on time, and for the convergence process, it's a little tricky. So we use some perturbation results by some curves at this point, and it's a little tricky, I would say. And same thing for the others. So after beta 2 over j minus 1, because now it's as if the first node is removed from my network. And now I'm just as the previous situation, except I have j minus node, minus 1 nodes outside, and so on and so on. And in the end, everything is flat, except at the last one, which is at beta j. And this is a picture. Okay. So it just as if I had two nodes here, j and j plus 1, and the others do not exist. Okay. And so you have multiple side scales here, and the tricky thing here is that you have equilibria even on this time scale. And this time scale is not nice at all to work when you do stochastic calculus. This is annoying time scale to deal with. We had many failures just because the fluctuations are a little tricky here. And so this is not the easiest part of the study, I would say. Okay, so in this case, if I'm assuming that my beta j is less than 1, then basically on this time scale, nt, Lg of nt is of the order of n beta j. Lg plus 1 does not change, it's of the order of n. And more interesting, that the others are just distributed as geometric random variables. And if you look closely, if you take your microscope, and you look at the behavior of this Lg, these are only MM1 Qs in equilibrium, and the service rate depending on time. So for a fixed time, let's say, for a time scale which is slower than that, then you have a kind of local equilibrium, which is an MM1Q. So you have a real stochastic averaging phenomenon here. Okay. Okay, so basically the star network is equivalent to our two-node network we had before. So, okay, conclusion. So, for this algorithm, these processes, you have to realize that you have to deal with multiple time scales and multiple space scales. And as soon as you realize that, then things can be put in order that you can understand the picture. Not the whole picture probably, but a significant part of the picture. And I've been using this F sharing. It's not the way it's used by the Rabat or the Damon. They are comparing log and so on. It's not exactly the capacity like when you do round robin to model. You do process sharing to model round robin. But basically, in our opinion, it should not change the basic behavior. But if you take this log policy that are used in wireless technology, you should have the same phenomenon. Okay, at least n power t is an interesting time scale to consider if you want to understand these things. Okay, further work. We have been frustrated because we tried to look at some second-order results, and as I mentioned, because of this strict time scale, it's a little more difficult. And our main objective now is to look at what wireless network people are looking at just when you have schedules, because you have two. For me, you have two components in these models. You have the schedule, the choice of function. So usually they are studied at the same time. In our case, we choose of not considering schedules, but just looking at the choice of the function. What is the impact of that? And now the thing to do is just to consider both of them, see how we can manage to understand properly what's going on in this network, especially these effects of large routing times that are observed when log policies are used. It would be interesting to see what's going on. Okay, so I guess it's finished.
Questions?
So either in your work that you've done here, or even just more generally, I'm wondering if there's like if there exists a framework to study the different time scales at the same time from like a stochastic process convergence framework.
It doesn't exist. There are some methods. This is stochastic averaging methods, but it's like large deviations. You don't have a large deviation method. You have a set of techniques that you can use to study large deviation, but you don't have specific, because it's highly dependent on the stochastic process you use. Here, for example, we have not been able to use these methods, but there are several of them. So I mentioned them by Fredin and Wenzel, by Struck-Varden Papanicolaou, where they have some basic method, but there is not a general method. It doesn't work.
But I guess I'm more general. So you're proving 3 different weak convergences, essentially.
Yes.
Is there any? Do you think there's any hope, or did you at all think about? Could you come up with one single time scaling function to prove a unified?
Yeah, this is what you. Yeah, when you study this process, you would like to do that. Just to study everybody at the same time and say, well, that's finished, I'm done. No, it doesn't work like that, unfortunately. And this is why it's tricky when you have stochastic averaging context. So it's known in loss networks when you have a rapid time scale and you have the macro state, which is evolving on the slower time scale. But the rapid time scale, the equilibrium, depending on the macro. So now in this case, it's not difficult, but in other situations, it's not so easy. Except that the intuition is so clear that say, oh, I would love to have that and to study them at the same time and so on. But you are not working on the same time scale. So you have to choose one and just to manage to control the other. You cannot do that just because of the problem. Although it's a temptation to do that, of course, because you would like to do the same thing. Say, oh, well, this one is at equilibrium, this one change, and then I can do both of them. No, it doesn't work. There are some techniques which are used to do it. So it's Struck, Papanicolaou, and Varden who had some martingale arguments, and they have been used also by Tom Kurtz in loss networks and several of his co-authors. But you just have it's a case-by-case setting. You don't have a general result that crushes everything. I have not seen it, at least. And if you remember, there is a translation of these problems in the PDE's world. It's a singular perturbation problem, and the literature is huge. I can tell you, compared to in stochastic literature, it's a very small one. You have tens of books on these problems, and situations are so different that you have to deal with each of them. So there are some classification of the singular perturbation problem, but it's not so easy. And in the stochastic context, for the moment, it's scarce. I would say that for concerning diffusions, more or less, it's quite well known. You have Fredin who is still working on this result, and more or less they are looking at new recurrent cases, which are more stranger cases. But concerning jump processes, I consider that there's a lot of much more work to do to have something satisfactory, so that you can have a kind of toolbox to use when you encounter these things. And this is one of the things that we are doing with. I have several projects in this domain just to understand how we can do that in practice. Yes.
I think for the star network version, so you have changed the scheduling problem a little bit.
Yes.
I
can tell that, because it's funny, because Damon chose the sum of the rows equal to 1, and he took the rows equal, some rows equal, and this is why we have chosen not to look at that, just because it was we were forced to look at second order, and we thought that it will be so easy to handle. although we have an idea when the rows are equal, because you have seen correctly, I managed to have different rows, and there are some contradictions. So clearly, but yeah, I'm not sure that the sum of the rows equal to 1 is a good idea just to start with. So, and especially if you simulate them, simulating a critical system like that is just tricky. So I never say that I solved the Demon problem precisely, but it's okay. Oh, that's it. That's it. Okay.
Just a quick question. You described straight after each other the transient result,
Yes.
and then the heavy traffic result,
Yes.
which both had a very similar form.
Yes.
So was the technique for establishing the heavy traffic result influenced by the...
Oh, yes, of course. Yes, of course, because basically the idea is simple. When L2 is large, L1 is L2 beta. So you just have to manage the order of magnitude of L2, and to prove that, so we use the invariant distribution, the cycle formula for the invariant distribution, and we use the classical heavy traffic theorem, and so we present it like, so with the cycle formula, you are looking at the transient characteristic of your process. So if L2 on this cycle is large, then L1 should be L2 power beta, and then I will have it for the invariant distribution. So this is just, but I really say that this is the real result. That on this time scale, then I can control L1 and L2 on this, and this is how we did it. Otherwise, it's also one of the things that you would like to do. Just convergence of the invariant distribution is quite difficult in general, because it's there are several techniques, but it doesn't work like that. But here it was simple, given that we had this result on the hand.
Any other question? So let's thank the speaker.